start recording as well. So, syllabus is up because I wanted to remind folks of what is going to be happening over the next couple of weeks. We have homework just closed last night. I updated your grades this morning. If you have any questions about why you missed what you did, please let me know. Not everyone has finished with it, so I'm not able to talk about it in this medium, but I'm certainly able to answer questions. And your next thing is a formative assessment. That will be due Monday. And you should be able to do that already, but for certain after today. And I just opened homework 3, which will be over quadratic models. And that will be due on the 4th of November. So moving along. All right, I think that's what we had. I will let you know when example 6B is ready. That will be piecewise models, starting those next week. 6C is one that I'm not going to do in class because it only uses SAS. So I have a video about that I had recorded a while back, since I haven't changed that one in a few years. And then I will let you know when D is ready. So we're slightly out of order, but it's D is the last one because it's not in the book. It's something that I came up with after the book, and so it's after all the other content. So, and then we're heading towards Thanksgiving. We're getting there. So, anything I'm forgetting, or logistics questions, any of that stuff? Nope, we're good. All right. Then, talking about polynomial models. That's what we were talking about. That sound about right? Let's see here. Do you want to pick up where we left off, or do some more review? Re-go over? Start new? There's lots of choices here. What's the vote? I'm watching the chat, or you can use your voices. Take your pick. We trust you. Quick review. I'm happy that you trust me, though. That's very nice. Okay, then let's see here. So the idea of polynomials, quick review, is that we are trying to approximate a nonlinear function with a squared term, a cubed term, and so forth. You can go up to a number of occasions -1 in terms of the order of the polynomial. -1 because you already have an intercept. So if I had 2 occasions, all I can have is a linear slope. So I have 1 intercept, 1 slope. It will perfectly reproduce the 2 means. If I have 3 occasions, I can go intercept, linear, quadratic. That will perfectly reproduce the 3 means, and so on. So there's really no point to fitting a polynomial function if you saturate it, but usually we can get away with something that is an order simpler than what the ultimate highest one would be. So like quadratic or cubic is really in practice what I see. The rule for those is that we have to multiply the quadratic coefficient by 2 in order to talk about how it changes the linear slope. That is because the quadratic coefficient itself is half the rate of acceleration. And I'm not going to say deceleration, I learned, but I didn't update the slides. Half the rate of acceleration, or negative acceleration as it were. That's because we're talking about the second derivative of the function. In terms of examples, there's really 4 patterns, and the same patterns hold for quadratic terms as hold for interaction terms, because quadratic terms are interaction terms. It's time times time. So the intercept, once we have time in the model, is conditional on time 0. If you only have a linear slope, then it's unconditional. Once we add a quadratic slope, then the linear slope becomes conditional on time 0 as well. And the term for that is an instantaneous linear slope, because it's not describing the change from 0 to 1. It's describing the rate of change exactly at 0. More technically, it is the slope of the line that is tangent to the curve at that point. And that's what these little dashed lines here are on slide 14, to the best of my PowerPoint drawing ability. So at time 0, in this picture, the slope is 4, and it becomes more positive by twice the quadratic for each unit in time. So the slope is stronger. It's 4.6, difference by twice the quadratic at time 1. It differs by another 0.6 at time 2, and so on. So this curve I would call accelerating positive based on the shape. It's going to go up. It's going to go up faster as time goes on. Decelerating positive is what I would call this, because it is a growth trajectory, but it is slowing down. So the negative quadratic is working against the linear, and so the slope is becoming less positive over time. So I would not call this decline though. It's just that it's less positive. Eventually though, what's going to happen to it? Like if I follow this out to 6, 7, 8, where's this curve going to head? This is a gesture question. Down. Yeah, it's like. So for that reason, what goes up must come down, and what goes down must come back up again. Sometimes quadratic trends are theoretically dissatisfying because there's not a lot of behaviors that would necessarily follow that pattern. Like if you're tracking changes in learning, for instance, a quadratic model would predict that eventually kids not only slow down their learning, but then they forget stuff, like it comes back down. And that doesn't seem reasonable for a lot of applications. Some it does, but not always. Then these ones have negative linear trends at time 0. The one on the left becomes less negative by twice the quadratic for each unit in time. The one on the right becomes more negative. Okay. How's that for review? But does it work for age-related things? It could. I'm not saying that there's no situations, but I can think of very few examples of something to where it's like it would be a true parabola would make sense theoretically. Usually it's diminishing returns, which can be better approximated as an exponential model, or the cheaty version that I'm going to show you in example 6D, log time as a way to cheat your way into an exponential function. Okay, so then we talked about this last time, right? Things becoming conditional. I think there's a lag between my voice and your reactions. Is that accurate? Okay, yeah, that's what it is. I'm like, why aren't they reacting to anything? It's like, oh no, I just need to wait. The awkward part where we all stare at each other continues. That's Zoom for you, indeed. It could also be my internet. I don't know. We are making it work. That continues to be the theme. So the same thing happens in terms of conditionality on the fixed side as on the random side. So that's where we were talking. We mentioned 3 occasions are good. Is there room for overfitting the model? I'm not sure what you mean by that in this context, but I can tell you that if you had 3 occasions, then those 3 means would be perfectly captured by an intercept, a linear trend, and a quadratic trend. So it would just be a reparameterization of a saturated means model in that case. If you have 3 occasions in unbalanced data, then that would not be the case, because there would potentially be a different set of 3 occasions for each person, and then a quadratic trend might work to describe the trend that goes through all the separate points instead of just the 3 common ones if you had a balanced design. Is that what you meant? So 3 occasions equals saturated quadratic model. Yeah, so saturated means that you have as many fixed effects as you have means, and so the means will be perfectly captured by those fixed effects. A fixed quadratic model for 3 occasions would perfectly reproduce the 3 means because you're spending 3 parameters: intercept, linear slope, and then quadratic slope. You need more than 3 occasions if you want a predictive model, and yes, that was what he meant. Good. Yeah, like if you're trying to judge how well your function fits the means, you have to have room to be wrong. So you would need at least 4 occasions so that you would have some potential discrepancy. On the random side, though, there's a different rule in place. So let's pick up with that. So this is slide 16, and then we'll do some notation. Room to be wrong. Yeah, that's the way I think about it. Like if you picture, the line through the dots, it will perfectly fit the dots if you have a saturated model, but it will not perfectly fit if you don't. All right, so once we add a fixed quadratic term, the fixed linear term becomes conditional on time 0. We're good with that? Yes. Okay. So the same thing happens then on the random side. So if I have a random intercept only, that is not conditional on time. you can think of it as mean differences in that case because a random intercept only implies parallel trajectories. So people stay just as spread apart at time 0 as they would at time 1, at time 2, time 3. Once we add a random linear time slope, then the random intercept becomes conditional on time 0, in the same way that if we add a fixed linear time slope, the fixed intercept becomes conditional on time 0. So then it matters where time 0 is. You would have a different intercept variance at any point in time because people are spreading themselves out through individual differences in change. Same idea with the quadratic. Once we add a fixed quadratic, fixed linear time becomes conditional on time 0. If I add a random quadratic slope, then the random linear slope becomes conditional on time 0. So it especially matters then. And the rule for how many random effects related to time in terms of slopes that you can have is number of occasions minus 2, because you always have a random intercept variance and a residual variance to start with. So then the question is, how many more slopes do you have room for? And the interpretation of the corresponding random effect variances matched what the fixed effects mean. So if a fixed quadratic introduces acceleration, then a random quadratic introduces individual differences in acceleration. Here's some equations. Yay, equations! They're better than matrices, right? Can we agree on that much? Yeah. So hierarchical notation, continuing this, the traditional way of writing multi-level models. So we have at level 1, YTI. And by the way, you can pick whatever letters for subscripts you want. You are not stuck with IJ or TI or anything. And I would highly encourage you to pick subscripts that will remind people what your levels mean. Working memory is aided by using notation that is straightforward to capture. So YTI, time and individual in this case, is a function of 3 individual specific effects. So this is a random quadratic time model. So I've got beta 0, beta 1, and beta 2, and those all have an I subscript indicating that they can be individual specific. Question, can you have individual differences in quadratic slopes such that some people are accelerating positive and some people are accelerating negative? Absolutely. Yep. You could have a fixed quadratic that is non-significant, meaning like on average there's linear change and people could be going away from it, like accelerating up, or they could be decelerating down. So yes, absolutely you can. So these betas, are these fixed effects? Are the betas fixed effects in this notation scheme? They are not. What are they instead? I can think of a couple different words that would apply. Placeholders, that's what I have in the book. A container is also something, is the idea of a placeholder, like it's a backpack. It's like where you put your stuff in the level 2 model. SEM connection, there's one more. Starts with an L, latent variable, yes. These betas are latent variables. In SEM notation, these would be circles. And the mean of the latent variable is the fixed effect, and the variance of the latent variable is the random effect variance. So there's your connection to those words. Random effects and latent variables are the same thing. So these betas are containers, placeholders, latent variables that then each can have a potential fixed effect and random effect. Fixed effect at a minimum, random effect optionally. So then beta 0i is a function of a fixed intercept and a random intercept. So u0 is how far off the fixed intercept your intercept would be. And that is going to be conditional on time 0, given what's in the model already. Likewise, beta 1 is how each person gets their own linear time slope, and that in this model would have a fixed part and a random part. So gamma 1o is the average linear slope, and it is also conditional on time 0, given the quadratic term as a fixed effect. U1 then is how far off the average slope your linear slope is. So if there is, let me give an example. Let's say the slope is 8 and U1 is -2. So is that person declining or growing? If the fixed slope is 8 and u1 for a given individual is -2, how do we think about that? They're growing, but more slowly. Yes, exactly. So their slope would be 8 minus 2 is 6. So that person would still be demonstrating growth over time, just less growth than what's happening on average. And we can compute 95% random effect confidence intervals to describe whether some people are actually declining or whether just everybody is growing positively but at different rates. One more then, beta 2 is my quadratic time slope, and it has a fixed part, gamma 2O, and a random part, U2I. So then each of these starts with 0, 1, and 2 because it goes with which beta they're predicting in the level 1 model. Each of the fixed effects ends in a 0 because it is the starting point of that level 2 equation. Sometimes people refer to these fixed effects as the intercept of the level 2 equation, and I find that language confusing, so I try not to use it. But if you look at, for instance, output from the HLM program, they will use that term explicitly. Like they would refer to this fixed quadratic slope as the intercept of this level 2 model. So U2 then is a new random effect. This would give you individual differences in acceleration or deceleration. So you would have to know what the linear is doing to interpret what the pattern is, but there's only 4 choices. It's going to make the function more positive, less positive, more negative, or less negative as time goes on. How many parameters are in this model? Let's start on the mean side. How many fixed effects do we have? 3. Yep. In the model for the variance, how many variances do we have? We'll start with variances and then we'll do covariances. How many variances? 4. Yep. So how many potential pseudo R-squares would we have? 4. Uh-huh. Yep. Now, how many covariances do we have? We got 1 vote for 2, 1 vote for 3. Yeah, picture it is a 3 by 3 G matrix. Yep, it's 3 covariances. So we have the covariances among the U's because all the U's come from the same person. So G is always unstructured. So the diagonal would have the 3 random effect variances, the off diagonal would have the 3 potential covariances, and U's and E's never have covariances. That would like break the world. That's the definition of a level, is that it's separate. So all covariances would happen at the same level only for random effects that go with the same unit of sampling. So how many occasions do I need to fit this model, given that I have a random quadratic term? And feel free to, read from the slide as usual. How many occasions do I need to fit this? At least 4 to have the random quadratic. Yes. At least 4. And here is why. Y is coming in like 3 slides. I know I have a slide about that. So if it were fixed quadratic random linear, if I did not have this U2, then how many would I need? How many occasions? At least 3. Yep. Very good. All right, so here is an example sequence that you can use to decide how to augment your model. And this is the type of sequence that you'll get a chance to practice in homework 3. So the purpose of the first model would be empty means random intercept. Get your ICC. Find out how much of your variation is longitudinal versus cross-sectional as a starting point. Now we know this model is not likely to be sufficient, and therefore the ICC probably needs to change over time, but it is a starting point. Then I would do fixed linear time slope, and you can stare directly at the Wald test p-value for that because it's a fixed effect. So estimate divided by standard error gives you a test statistic, no problems. Once you add a random linear time slope, though, Then we would need to do a likelihood ratio test to evaluate that, and it would be 2 degrees of freedom because we've added a covariance with the random slope variance. Then I would go fixed quadratic random linear, which would allow me to then test the fixed slope by itself by looking at the Wald test. And then random quadratic would be after that, which would be degrees of freedom 3, because we would add one new variance plus the covariance with the two things that were already there. Now this sequence is one option. Another one that I have done in practice would be to go from empty means to fixed quadratic random intercept. Like if I know something's going to be bendy, I might put in fixed linear and fixed quadratic first. That way I can more easily check how much variance that those fixed effects explained, and then I might add the corresponding random slopes. So this is not like a hard and fast rule, it's just like one possible strategy. Alternatively, some folks like to start with the most complex model that they would entertain and then see if taking anything away hurts. Because like if you start at number 5 here, random quadratic, and you remove the random quadratic slope variance and its covariances, and the model fits worse. If that happens, you're done, because you know that you need that term. And if you need a random quadratic slope, that means you need the fixed quadratic slope that goes with it. If you have a fixed slope that goes with it, you need the linear term underneath it. And if you have a random quadratic slope, you need the random linear underneath it. Okay, does that make sense? Maybe? Okay. So yeah, it's everything is hierarchical in these models. So you don't have to go from the ground up. You can also sort of go from the top down. Question, do you kind of start with what you would think would be the most explanatory theoretically and then go backward or forward from there? Yeah, I think that's a reasonable thing. The pattern of means that you see in your data. So the saturated means model, if you can fit it, if you have unbalanced time, you can round it into convenient integers just to get a saturated means function. Like that should guide you towards like what type of family of change you have. And so I think it's a reasonable thing to do it, like start from an expectation as opposed to just starting with like nothing. The only catch is that in order to compute effect sizes, you usually need to estimate comparison models without that. So for instance, like if I think I have a fixed quadratic time trend, I'm still going to have to estimate the empty model so that I can see what the residual variance would have been that those fixed linear and fixed quadratic time slopes would have explained. Okay, other questions? Now, what I don't recommend is adding fixed and random effects at the same time. That is illegal in REML because likelihood ratio tests have to have the same fixed effects, but it also makes your results ambiguous as to which one helped. Was it the fixed effect, the random effect, or both? So you always start with empty model. Yeah, kinda. Empty model is something that like that would go in your results section pretty much for every multi-level sampling design. By the way, once you're reporting an intra-class correlation, there are no hard and fast rules about what is enough to continue doing a multi-level model or what is low enough that you don't have to. I see this in papers a lot. Like they say, oh, the ICC was less than 0.05, so I don't have to worry about it. Like, no. Your design effect that comes with the clustering, the nesting of observations within level 2 units, that design effect is a function of level 1 sample size per level 2 unit and ICC. So only an ICC of truly 0 would result in no design effect. So just as an aside. All right, so we talked about this, just putting the words on there. Once you have a random quadratic time slope in your model, both random linear and random intercept are conditional on time 0, so it matters where those are. All right, here is why you need the number of occasions that you do to fit different things. This is the exact same concept of degrees of freedom as you would have learned it in structural equation modeling. It is not different. So we're focusing only on the variances and covariances over time for right now. So this is a discussion about random effects, not fixed effects. So if I only have 2 occasions, in terms of the pieces of information that would go into allowing me to estimate my model parameters, I would have 2 variances and a covariance. That means that given that I have to have an R matrix, so I have at least 1 residual variance, then I only have room for a random intercept. Because if I tried to estimate a random slope as well, then that would take a random slope variance and a covariance with it, and I would be under-identified. So we have two parameters here, residual variance, random intercept variance, and there's 3 pieces of data. So they're essentially like 1 degree of freedom left over. If I have 3 occasions, then I have 3 variances and 3 covariances going into the problem. Now I have room to estimate both a random intercept variance and a random linear slope variance, or one kind of slope at least, doesn't have to be linear, and a covariance and the residual variance for 4 parameters in total. So I have 6, I can estimate 4. If I have 4 occasions, that's 10 pieces of information. Now I have room for a second random slope of some kind. And so then that brings with it the 2 covariances with the terms that were already there. So this would be consistent with a random quadratic change model. This would also be consistent with a change model that has 2 different kinds of slopes more generally. So in the next example, 6b, we'll do piecewise models, which are linear splines that divide time into sections. So like you could have a random slope for one part of the function and then a random slopes for the second part of the function if you have at least 4 occasions. And then you have room also to potentially add other things to your R matrix. Like you can have a residual correlation or something like that because you have 3 degrees of freedom left over. All right, so shorthand, n-2 for the number of random slopes related to time, n-1 for the number of fixed slopes related to time. That's the take-home message. And you remember this scary looking function? This is how the V matrix gets built under a random linear model. I got news for you. It's about to get worse. This is the one that the quadratic builds. So if you add a random quadratic time slope variance, then you are saying the variance changes over time in a function that has time up to the 4th power. So quartically, can I say that? Quartic? Sure, 4th it. So random linear implies a changing pattern of variance that is quadratic, parabola. Random quadratic implies a changing pattern of variance of time to the 4th. And the covariance function is pretty messy too. So, point of the story. Every time you're adding a random slope related to some predictor variable, you are introducing some kind of heterogeneity of variance across that predictor. Here it's across time, but it would be across any level 1 predictor that has some kind of random slope. So here are some rules, that guidelines in terms of what you can and can't do in terms of model comparisons. So on the same side of the model, lower order terms stay in even if they are non-significant. Meaning, like if I have a significant fixed quadratic slope, I keep the fixed linear slope underneath it regardless, because it's the same idea as having the main effect as part of your interaction stay in the model, even if the main effect is not significant. It's needed for the interaction to have the correct interpretation. Likewise, if I have a significant random slope that's quadratic, the variance is significant, I should say, then I would keep the linear slope underneath it because it is hierarchical. You can have a significant random effect even if the fixed effect that goes with it is not, and you would keep it anyway. So if I have a random slope of any kind, I have to keep the corresponding fixed slope with it because the random slope is always phrased as a deviation from the fixed slope. So if you leave out the fixed slope, you're saying that it would be exactly 0, and that is probably not going to be the case in most of the time. And so in terms of language, because of that rule, because if you have a random effect, you also need the fixed effect that goes with it, when you talk about the model, it is enough to just refer to the random effect. So like if I call my model random quadratic, that implies that I have a fixed quadratic. It also then implies that I have a random linear, which then implies that I have a fixed linear. So all of those things are hierarchical. You only have to refer to the highest order term. One thing else to keep in mind is that the correlations among these things are also going to be a function of where time 0 is. So among the intercept and among the slopes. So here's why. So let's say that I have just a straight random linear model here. People are growing at different rates. If I decide to put time 0 here, the correlation between the intercept in terms of where people are on this y-axis and the linear slope would be about 0. because there is no difference across people in the intercept at this point. If time 0 were back here, then I would have a perfect negative correlation between the intercept at this time 0, because the people who are highest are changing the least quickly. They have the flattest slopes. But if I put time 0 over here, now the correlation is a perfect positive one, because the people who are highest at this point have the steepest slopes. So there is not a single right answer to what the correlation between an intercept and a random slope will be. It depends on where the intercept is with respect to the predictor that has a random slope. So if you want to interpret the correlation between your intercept and your slopes on the random side, you would need to be specific to the time 0. So it's not the intercept slope correlation, it is, performance at the beginning of the study, or performance at this particular age, something like that. I would make the time 0 contextual and conditional on that. Another issue is that your random slopes, if you have a linear and a quadratic model, are going to be highly related, because time and time squared are pretty correlated. So that can sometimes cause issues. So I have here 3 different centering strategies with respect to where time 0 is. So for our 6 occasion example, this is the one that we're working with right here, where we have time 0 at the beginning. And if I do that, then I would expect a positive relationship between my linear slope and my quadratic slope. So the linear values that are in this column are on the x-axis, and the values that are on the quadratic column are on the y-axis. If I center such that time 0 is at the end, that's going to introduce a negative correlation between the two slopes. And if I mean center time, so that would be time 3.5 in this case, then the correlation between the linear and the quadratic slope will be minimized. So some textbooks, for this reason, recommend mean centering time, so that you're reducing some of the correlation between time and time squared, potentially preventing estimation problems. Now, there's a downside to this. If I mean center time, what is my reference occasion? Vladimir's laughing. What's my reference occasion if I mean center time? Time 3.5. Like, that would be what time 0 is. That would be where my intercept is. So I would have individual differences at an occasion that doesn't exist. I don't love that. I gotta be honest with you. I don't. So in practice, I tend to ignore this problem and put time where I want it to be. But if you end up with random slopes that are perfectly correlated, that will break things. So you'll get an error message that your G matrix is not positive definite. That happens usually for one of 2 reasons. One of your random slope variances went to 0, or one of the correlations among your random effects went to a boundary, a -1 or a 1. So mean centering the predictor that has linear and quadratic slopes attached to it can be one way to solve that problem. All right. Want to see an example? Yay, examples. We're back to example 6a. And by the way, I noticed that the formatting on this document had gotten screwed up on the version that I posted. I think I reposted it Tuesday after I fixed something, so I just fixed it a little while ago. So this should be, my version should be the one that is currently on the website. So they should be back in sync here. So we went through this example last time up through, I think, random linear, and then we did just a little bit of quadratics. Does that sound right? Are we good with that? Can we jump into the quadratics, or do you want to look at any of the earlier models again? We're okay. All right. We're all okay. So one thing then that is going to be relevant today is this stuff right here. So I am creating session-specific dummy codes that are going to be used later on in testing absolute fit. So I did that here in Stata, and I did the same thing in R. Come on, there we go. I'm sure there's faster ways to do it, but my code is meant to be transparent, not to be efficient. Let's put it that way. So we will see those in action here in just a bit. All right, let me get to the quadratic models. Just saw it. There we go. This is page 9. There we go. So I have time as my predictor here. I don't have the centering in the model, but that is something that I would have to either put in the equation or put in the text. Why does this thing keep doing this? There we go. So we can create a quadratic term without having to make it for sure with respect to the fixed effects. So this is Stata code here. So we have times squared as a hashtag, but the random side won't let you do that. So I had to make times squared as an actual variable in my data set for Stata to allow me to give it a random slope. If there's a way around that, please let me know, but otherwise I'm just like, all right, fine, I'll make it. So this one also, the other piece that you need to make sure that you have, Stata folks, is this option, covariance unstructured. That is what introduces covariances among your random effects. It is not a default. Otherwise, if you run it without this, you will get your variances, but not your corresponding covariances. And we're still using an independent structure for the R matrix for right now. So let's look at the output. So constant is 1945. So as a reminder, this is response time in milliseconds to a speeded task. So what does that number tell me? 1945 is what? Response time at time 0. Ding ding, yes. So that is at session 1, the first time they practiced this task. What is the difficult in the code for? Great question. So certain models take longer than others to estimate, particularly in Stata for unstructured models, they take a long time. And I ran into this problem in a different context. I was fitting multi-level Tobit models for censored data, for censored longitudinal data, and I came across an option that tremendously helped in that case to speed up estimation, and it is the word difficult. So I've just started sticking it places, hoping that it would help. I don't think it hurts anything. But since this model has 3 random effects to it, and random quadratics in particular can have convergence problems, I have dealt with that in building your homework, of course. I wanted to throw it in here to help. So that's what it's for. It changes something. Sometimes your model is still difficult even when you use the difficult options. This is true. Yeah, random effects break models. Like that's the general principle here. So the more random effects you have, the harder your model is going to be to estimate, and the more likely things can have convergence problems. Start values are also something that you can do to speed things up. That's not something I know how to do in mixed, but I'm sure there must be a way. 10, have you seen that before? Inserting start values in mixed code?
I think difficult actually sort of starts there. It starts, I think, with the fixed effect solution, right? So Vladimir's dropping links in the chat. So
Excellent. R maximize. Oh, is that the difficult option? Is that what that link is for?
Yeah, I think that's something similar to the options we have for optimizers in Elmer, like the differences between Neldermead, Bobby-Qua, and the optimizer by default. So in that PDF, they explain what difficult is doing
Thank you.
related to optimization.
Perfect. Thank you for sharing. See, Zoom is good for things like this. I like the ability to share resources in the moment. Yes, it does add start values based on a model with just the fixed effects. Usually, though, it's start values for variances that will make a difference in terms of speeding things up. So I know how to do that in M+, and in SAS. I don't know how to do that in Stata and R, but another fun thing for me to learn. Yes, so 1945, that's the expected response time at session 1, which is time 0 here. And it is not the exact mean at session 1, it is the mean that is predicted by the function. So it has room to be wrong, since we have 6 occasions and only 3 fixed effects. Minus 120 is the linear slope. What does that one mean? Fixed linear time slope of minus 120. What does that tell us? Slope at time 0, the amount of change that applies to everyone. Both of those are true. Yeah, that is the average linear slope of the individual specific linear slopes. It is also the expected slope at time 0 specifically. Yeah. Then that leaves one more fixed quadratic of about 13.9. Let's call that 14. What do we need to do to that number to interpret it as how the linear slope changes? That one I need to multiply by 2, not squared. Yes, it is the marginal quadratic, or the average quadratic. So this would be the average rate of acceleration or deceleration. What it does is make this negative linear slope, I would call that less negative by 28-ish per session, per unit time. Yep, it changes the linear slope at each occasion by 14. So it is a constant change to the change. It's unconditional. So the quadratic is not conditional on time 0 because it's the highest order term. So it is a constant change of the change. Then we get down here into our random effects parameters. So this is the ingredients to your G matrix, the results of that. Note that it puts it in a different order. So time and time squared have their random effect variances first, then the random intercept variance, and then all the covariances. So like in SAS, it goes in the order of the G matrix, and in R, it's different yet still. And then residual variance down here, as usual. These are covariances that are given directly in the output. I asked for correlations of my G matrix, so that's this piece of code right here, gives you the correlations among your random effects. So you'll note this one, time and time squared have a very strong negative correlation. That is to be expected since they are highly related variables. But it's at least enough to where it didn't go into negative, non-positive definite, excuse me. I have the V matrix from R below because it printed in scientific notation, so it's not very useful to us. And then here is the model implied V matrix instead. So the pattern of correlation that this model predicts over time is heterogeneous, and it depends on exactly which 2 occasions they are in terms of what that correlation is predicted to be. Likelihood ratio test. So 3 degrees of freedom for this because we added a random quadratic slope variance and the 2 covariances with the random effects that were already there. Then I am doing some saving of stuff to compute confidence intervals because we can have one for each. So I had to find the stuff in the output first and then save the 3 fixed effects. So those are listed in the first 3 spots. Then we get into all the variances and covariances. I had to turn the numbers up here into variances. So what you get by default is the log of the standard deviation. I checked to make sure those were mapped correctly, and indeed they were. And then here are the confidence intervals that the code below is computing. So the idea of a random effects confidence interval, it's a way of conveying what the size of the random variance is actually doing in the scale of the original variables. So like a variance of 276,000 is not a number that most people can do anything with in terms of interpretation. But if you take the square root of it, that turns it into a standard deviation. And then you have the fixed effect as the center of the interval and about 2 standard deviations around it, plus or minus. That gives you the expected range in your sample of what that parameter would be. So for the intercept, for instance, the expected range is somewhere between 916 milliseconds and about 3 seconds, 2900 milliseconds. So that is the range of response time that is expected at the beginning of this task. The linear slopes ranged from negative 436 milliseconds per session up to 194. And that means that some people are improving, since this is response time and negative slope means improvement, but some people are actually getting worse. And if you look back at the original data, like the spaghetti plot, indeed, there are some people who are heading up to start with rather than heading down. And then the quadratic term also has an interval because it has a fixed effect and it has a random effect variance around it. And so it ranges from negative to positive as well. So the two work together. You would have to like come up with a prediction that involved like a particular number to be able to describe the pattern, because a negative quadratic could slow down a positive function or it could speed up a negative function. The two both have to be known to figure that out. So then the rest of this code, Stata folks, you should be able to repurpose without changing anything. So once you figure out like the numbers that you need to do math on in this table and save them to these variables, then it will do all of that for you. All right. Any questions from the Stata folks? And then we'll get to the R stuff. Okay. Yeah, the code is pretty straightforward once you get used to mix. That's the good news. In Elmer is what I'm using here. So note this option that's in this example. You need this for your homework 3. The instructions say so as well. You end up with different results if you don't use this. So I have the time squared inside the parenthesis here. That's the random part. I have the time squared outside the parenthesis. That's the fixed part. What was this called? Inhibitor, right? Inhibit function or something? Yep. That's what the I stands for. So I have asking for -2 log likelihood as usual, asking for the output, and then the Renova function tells us about the likelihood ratio tests. So the only thing that I'm showing here is the V matrix because this wasn't printed well out of Stata. So this is the model implied pattern of variance and covariance over time. And this is how it got computed, is this big nasty function right here of time to the 4th power involved. Here are the rest of the ingredients for building confidence intervals in R as well. And I don't have a function for this yet because it would be too difficult, I think, to figure out like which fixed effect goes with which random effect if they're not in the same order. So I don't have that yet, but if you're feeling industrious, you can go ahead and make one. But this code should work right there. Okay. Any questions on R code for that? All right. Then a couple other things. So this model, up to this point, has not dealt with anything with respect to the R matrix. It is using a diagonal independent structure such that we're assuming what the E variance that's left over, so the E's are the deviations around the line, the E variance is the same across time and the same across people, and we're assuming that the E's are uncorrelated. So all the reasons why people had occasions that would be related within persons is supposed to be in the G matrix. We can test whether that is the case. So I tried adding an AR1 correlation here. So I switched the type in Stata from independent to AR1. And to do the same thing in R, unfortunately, I had to switch packages. So the Elmer R matrix is diagonal only. That's the only choice that you get. So to introduce heterogeneity of variance or any kind of residual correlations, we need to switch over to the LME package within the LME function, within the NLME package. And so this one looks a little bit different. Rather than like REML equals true, it's method equals REML. There is a fixed part to it that's explicit and a random part to it that's explicit as well. So it's rather than one formula, it's separated into two. The correlation function here, this is the AR1 that I wanted to add, and it worked out to be estimated as 0.17. So this would be the expected correlation between occasions that are 1 unit in time apart. I would square that to get the expected correlation 2 units in time apart, cube it for 3, and so forth. So then the rest of the model output looks pretty much the same. So the marginal V covariance matrix now has that extra component that's allowing an extra correlation of residuals. In order to do a likelihood ratio test, though, because the random quadratic model was estimated in Elmer and this one was estimated using LME, I had to re-estimate the random quadratic in LME so that I could get the likelihood ratio test to spit out nicely, and here it is. So this version of it is using ANOVA rather than RANOVA. RANOVA is with Elmer, so you remember the R's go together. So what does this tell us? A p-value of 0.15 and a test statistic of 2. Yep, not better. That's exactly how I would phrase it. Adding this new parameter did not make the data taller. It did not improve the log likelihood. So I say fine, good enough. So the random quadratic model that we ended up with, this one's not a significant improvement. I'd say that's about as highest as I would go based on the patterns in the data. But what I don't yet know is whether it actually fits in an absolute sense. So graphically, I wanted to make a few plots here to illustrate what these models are saying. So the black line with the squares here, this is from chapter 6 of the book, by the way, that is from the saturated means model. So that is spending all 6 parameters to perfectly reproduce the means, and the functions are then going to try to reproduce the means when we have our polynomial models. So empty model is this line right here. It predicts no change over time because it just has a fixed intercept in it. The linear model is the dotted line with the triangles. So that one predicts that as time goes on, if you let these people continue practicing this task after 6 sessions, that they would continue to improve at the same rate. So seems unlikely. The diamonds is the fit of the quadratic model. So that works decently well. It's a little bit off on session 5. 5 was a little bit unexpectedly high. But the problem, theoretically, is that it predicts that response time would go back up. So people would start getting worse at this task instead of better if we continued that function. So that is less than ideal to me. So how well do you think the black line with the squares, the saturated means, is approximated by the quadratic? Stare at that for a second and I will answer Vladimir's question.
So, now that you are mentioning this problem that the prediction is increasing, however, in our data we don't have such values, right? We don't have session like 7 or 8. So theoretically, that may be that line is not the best one. However, given that we don't have those values in our data, do you think that can be an issue later? For example, if we want to predict something?
I think that an argument could be made either way. So I agree with you that, like, why am I worrying about sessions 7, 8, and 9 if they don't exist? Like that seems like a problem I don't need to solve. So from an empirical point of view, yeah, the quadratic looks like it's doing a decent approximation of this function. But there are folks that want their models to they want it to be meaningful. And so that would be a deal breaker from that perspective.
Okay, gotcha. Thank you.
Yes. So does it matter if your model predicts wrong things outside the range or your data, or you just want to maximize its prediction? Yeah, it depends, I think. If you were trying to anticipate what would happen in a new study that was longer, right? I don't think this is a good model to anticipate with, because I wouldn't expect people to suddenly increase in response time again. I would expect something where it levels off and kind of stays there. So from that perspective, I don't think it's as useful. No, same questions. you're all thinking about the right things though, and that's the important part. So what we don't yet know is, in an absolute sense, how well this quadratic function fits those means. Like, I made a picture. Now, can I use a likelihood ratio test to answer that question? Shaking heads. My question is, how well does the fixed quadratic part of this model reproduce the saturated means? Can I use a likelihood ratio test for that? Not in REML. That is correct. If we were in maximum likelihood, we could, but not in REML. Does that mean that I don't have to worry about testing absolute fit? Oh, sorry, can't. I'm in REML. I can see that being used nefariously. AIC and BIC unfortunately can't use those either because they start with -2 log likelihood as their core ingredient. And those log likelihoods in REML are not on the same scale if the models differ in fixed effects. Multivariate Wald test, ding, ding, ding. That's what we're gonna do. So this is not in the book because I didn't know this trick when I wrote the book. So this is another thing that will go into the second edition that is theoretically being written. Theoretically. I signed a contract like 6 years ago. It's coming along great. Hi, Taylor and Francis. I hope they're not watching my YouTube channel. I'll get right on that. So the next set of models is going to answer that question. This also has connections to the world of SEM. So in this example, I am adding 3 new dummy codes. These are the dummy codes that we added at the code at the very beginning. They are literally, if it's session 1, it's 1, and otherwise it's 0. If it's session 2, it's 1, and otherwise it's 0. I am essentially filling in the holes to get back to what is functionally a saturated means model. Because now I have 6 parameters. I have intercept, linear, quadratic, slopes, and then I have these 3 dummy codes. That is going to perfectly reproduce the 6 means. So the question then is, does adding these 3 new dummy codes help make the model fit better? If it does, then my model isn't good enough by itself. That's the logic. So we are saturating the model for the means. The result is that the rest of the parameters are pretty much uninterpretable at this point. So the goal of this is to test whether they are sufficient not to interpret things from this model. And it doesn't matter which 3 dummy codes it is, by the way. The key idea is that I want to ask for a joint test. So that's how I do it in Stata, first with the option test of the 3 new dummy code slopes simultaneously. Because if as a set they're significant, that means they help the model. That means my function is not good enough to reproduce the means yet. So survey says an F of 3 with a p-value of 0.03. Bad news. Same result in R. Back to Elmer for now. So the way that this test statement works, by the way, is that you list the slopes that you want to test and set them equal to 0. And then that gives you a hypothesis test for those 3 slopes at the same time. And the parentheses delineate degrees of freedom. So it understands that this is an F test, that I want an F test for the 3 slopes because of the parentheses. In R, the contest MD function, this is out of the Elmer test package, is what I use to do this. It's more tedious, but I haven't found a way around it yet. So what these codes are doing, like this is for the first dummy code right here. It is the 4th fixed effect in the model, so I turn a 1 on there. Then I want the 5th fixed effect in the model, and then the 6th. So I'm asking via this test a joint test of whether those 3 slopes are 0. where again, the parentheses delineate degrees of freedom. So the fact that there's 3 of these C things in here means that it understands I'm trying to lump together 3 slopes to get a joint test. And I get the exact same result. So significance is bad here. And by the way, it doesn't matter in this model which 3 demicodes you pick. So just to demonstrate that, I did the other 3 for sessions 4 through 6. Now the other parameters in the model have again rearranged themselves based on which ones I picked, but the same exact hypothesis test results. So this is how you can test absolute fit of your fixed effects to the pattern of means if you are using REML. And this is only possible to do if you have balanced data though. If you have unbalanced data, then there's really not an analog. That would be obvious, let's put it that way. There may be ways to work around it, but nothing that would jump out at you. So the connection to SEM, by the way, when you set up these models as structural equation models, you have to shut off the intercepts that go with the observed occasions because you've pushed all of the information about the means up to the latent variables. To allow essentially like a deviation, like if your model doesn't fit like a particular occasion, if you allow that intercept to be estimated, that is functionally the same thing as what we're doing here. Like if I will go back to my picture, where the issue is in this function, it looks like, is the quadratic doesn't match like the middle two. Like session 4, I think, is like where it's the most wrong. I could leave in the demicode for session 4, and that would essentially fill in the gap between what my line is trying to do and where the mean is. So I can turn on an intercept in an SEM context. I can estimate a slope for this demicode in this context. So in a model like this, it doesn't matter which occasions you pick. You just need to pick as many as it takes to saturate up to the means. Okay, does that make sense? Okay, so what we've learned so far is that our model does not fit the mean pattern very well. This one. What I was looking at is the variances. So this plot on the bottom is about the variance that is predicted by each of these models relative to the right answer, which is given by the unstructured model. So the black line with the squares, again, is the unstructured model variances. We saw that pattern earlier in the handout, that they are heading down over time. People are getting more homogeneous, less variable as time goes by, or not time, in this case, practice. The random intercept model is the straight line here. It predicts no differences in variance over time. That's compound symmetry. The random linear, given by the triangles, that is the one that looks like a U. So you can see that it is predicting variances would decrease, and then at some point the function reverses. So if you kept going, it would predict increasing variance over time. The one from the quadratic model is the one that goes off the chart here. That's time to the 4th. So it predicts this quartic pattern that looks almost like a vertical asymptote. So how well did these do? Can I use a likelihood ratio test to answer that question? Can I test whether my random quadratic variance model is a good approximation to the unstructured one with a likelihood ratio test? That's my question. I can, because in REML you're allowed to compare different models for the variance, but I have to keep the fixed effects the same. That's the only catch. So I can't compare random quadratic back to saturated means unstructured, because those differ in their fixed effects and their random effects. But I can if I fit fixed quadratic with unstructured. So that's my last one. So I have this thing in Elmer. Let's see here. There you go. Nope, down here. I'm like, no, I don't have Elmer. Here we go. So this model in Stata has fixed quadratic time with an unstructured R matrix. as point of comparison. I had to switch back to GLS and the NLME package to do that within R. So the model, rather than having factor here for time, is my fixed quadratic model, and this part gives me the unstructured equivalence as well. And then I reran the random quadratic in LME so that I could get the likelihood ratio test. So in LME, in that package, it's ANOVA rather than RANOVA. And here's what I got. Survey says the comparison is significant. What's that tell us? Good news or bad news? Yeah, not good enough. So I would say that unstructured, it fits significantly better, or I would say that random quadratic time fits significantly worse. So 0 for 2 on test of absolute fit with my polynomial model. Wah, wah. But fortunately for me, I have about 60 more pages of handouts where I can try other ones instead. Yay! But not today, I promise. It's better than linear. Yeah, so the distinction that we're making here, there's tests that assess relative fit, and then there's tests that assess absolute fit. So relative fit is like, is quadratic better than linear? I can answer that question, but I can't say, is quadratic good enough? That's absolute fit. So that's what we're trying to do here, is the latter. Are the means sufficiently well approximated by a fixed quadratic time model? And then are the variances and covariances sufficiently approximated by random quadratic and linear time slips? That's the question. So far, the answer is no. All right, we made it. It's the end. And by the way, example results sections for all of the models that are discussed in the book are in the book. For the examples that are not in the book, then I will have example results sections at the end as usual for those. All right, questions? Feel like you can do this? I feel like you can. I feel like we're going to find out. Homework 3 is open. You can get started on it or you can put it off, your choice. It's due November 4th. Next thing is formative assessment number, what are we on, 4? I don't know, one of the middle ones, whichever one you haven't done yet. That will be due on Monday, so we can talk about it on Tuesday as usual. All right. Would you like 4 minutes of your life back? I'm so generous, I know. All right. Thanks for being here, folks. Let me know if you need anything. And I hope you all have good weekends. Bye for now.